Now the next topic we have to start the electrostatic potential at a point P due to the electric dipole. So in the previous topic we have studied the electric potential due to a single point charge, and its value we have got here q by 4 pi epsilon naught r, where q is the that source charge. Now we have to find the electrostatic potential of point P due to the electric dipole. An electric dipole is containing one positive charge plus q and one negative charge minus q. So here the point P is the point at the position vector r from the center of the dipole, because O is the center of this dipole and OP is the distance. It is given by distance vector r. The angle theta between the dipole moment P vector and the position vector r is, because this is P dipole moment vector and this is r, so the angle between P and r is theta. OP distance is r. This PA distance distance is OP distance minus OM, because we are considering this dipole is very short, very small, and this PA distance is almost equal to OP distance minus OM. So this will be equals to R minus L cos theta, because this is L, this will be L cos theta. This is also L OB distance and this ON is also L cos theta. So R1 vector will be, R1 distance will be R minus L cos theta. In the same way PB that is R2, that will be OP plus ON, that will be R plus L cos theta. So R1 we have got, R2 we have got. Now since dipole is considered to be very small as compared to position vector r, so r is much larger in comparison to L, that is the length of the dipole. Now the electric potential at point P due to this dipole is given by V of P, that is equals to V electric potential due to minus q charge and V of plus q charge, sum of the electric potential of two charges. So this will be minus q upon 4 pi epsilon naught PB distance, and this will be plus q upon 4 pi epsilon naught PA distance. So in this q by 4 pi epsilon naught is coming out to be common, and we will put the value of PA and PB. So this will be finally coming out this expression, V is equals to Q into 2L cos theta by 4 pi epsilon naught R square minus L square cos square theta. So we know that P dipole moment vector magnitude is Q into 2L. So the magnitude of P multiplied by cos theta upon 4 pi epsilon naught R square minus L square cos square theta. Now we are knowing that since dipole is very small as compared to position vector, so R is much larger than L. So R square is also very large, very large in comparison to L square. So L term will be neglected. So L cos theta will be neglected. We are getting left with R square term. So finally the potential V due to the dipole, electric dipole, is coming P cos theta upon 4 pi epsilon naught R square. So what do you mean by P cos theta? P cos theta represent the P vector dot product of the unit vector along the position vector. So P dot R vector upon its magnitude. This R is the unit vector along the position vector OP, that is R vector. Because we know that the dipole moment was in this direction, that was P, and the position vector was here, in this direction and this angle is theta, this will be P of cos theta, because this we are considering this point as P, so its component theta component will be here P cos theta, which is coming. Now the finally P cos theta is the P vector along this unit vector R, because this direction is the direction of this unit vector R. This direction is the direction of unit vector R. So this will be P dot R unit vector or P R vector upon its mod value. So electric potential at a point P due to dipole is given by V is equals to P vector dot R unit vector R cap upon 4 pi epsilon naught R square. So this will be P vector into R vector dot product upon 4 pi epsilon naught R cube. Now here we have two cases because of the cos theta term. Case 1 is if the point is at dipole axis. It means if the point is on the axis of the dipole, then theta will be either 0 or pi. If we are saying that if this point P is on this axis, on this dipole axis, then the direction of this dipole moment vector and direction of this position vector P will be having the angle between them either 0 or 180. So this we are getting theta will be either 0 or 180. So cos theta we are getting plus 1 or minus 1. For cos 0 we are getting plus 1. For cos pi, cos 180 we are getting minus 1. So the value of potential of the point P will be V of P will be plus minus dipole moment P small p upon 4 pi epsilon naught R square. Second case is if this point P is at equatorial plane with respect to the dipole, then equatorial plane is the plane which is perpendicular with respect to this axis of the dipole and it is passing through the center of the dipole. It means the point is exactly perpendicular and passing through this center of the dipole here. Then this is the equatorial point. At this the angle theta between this dipole moment vector and this position vector will be 90 degree. Exactly 90 degree angle will be forming. So theta angle will be 90 degree. Cos of 90 is 0. So here the point P at equatorial point, this potential, electric potential will be 0. So electric potential at axial point due to dipole is either plus minus P upon 4 pi epsilon naught R square, whereas electric potential at equatorial point due to dipole is 0. There is one note: electric potential due to dipole varies inversely proportional to the square of the distance of point from the center of the dipole. It means V is directly proportional to 1 by R square. Now the next topic is electric potential due to system of charges. So in this we have taken 3 charge. We have supposed there are 3 point charge Q1, Q2 and Q3 at a distance R10, R20 and R30 respectively from point P. Here we have taken point P whose position vector is R0, and there are 3 point charge Q1, Q2 and Q3 having position vector R1, R2 and R3 respectively, and the distance of this point charge from point P is R10. From point charge Q2, this point is R20 distance. From Q3, this point is R30. where the electric potential is to be find out. So at point P we have to find out the electric potential due to all three charges which are kept in this 3xyz plane, xyz three-dimensional figure, sorry. So now electric potential at a point P due to charge q1, small q1, that will be v1, that will be plus q1 upon 4 pi epsilon naught r1 naught, distance from this charge. Similarly, the value of electric potential at point P due to other charges, they are v2 is equals to plus q2 upon 4 pi epsilon naught r2 naught, and this v3, that is minus q3 upon 4 pi epsilon naught r3 naught. Using the superposition principle, we obtain the resultant electric potential at point P, that is Vp, is the sum of all the three individual potential due to all the three individual point charges, that is v1 plus v2 plus v3. So Vp will be 1 by 4 pi epsilon naught q1 by r1 naught plus q2 by r2 naught minus q3 by r3 naught. Now we are generalizing this formula for n charges. We get the potential, electric potential at point P due to n charges will be 1 by 4 pi epsilon naught summation I from 1 to n q of I r I naught. This is the expression for electric potential for the system of charges. Now we have to start this next topic, equipotential surface. Equipotential surface, as the name suggests, it is the surface, plane surface or curved surface, which are having equal potential at every point on the surface. So its definition is given by: an equipotential surface is that surface on which at every point on the surface will have same potential. It means every point on the surface will be having the equal electric potential. So this is the definition for equipotential surface. Now next thing is potential difference between 2 points A and B is equal to the amount of work done in carrying a unit positive test charge plus Q, that is plus 1 coulomb, from A to B. We already studied this formula, that VB minus VA, final potential minus initial potential, that is equals to work done from A to B in bringing this plus 1 coulomb charge from A to B. So here, if point A and point B lie on the equipotential surface, then potential of point A will be equals to potential of point B. That means VA is equals to VB. So equation 1 will become 0. This equation will become 0 because VB and VA are having same potential. So VB minus VA is equals to work done from A to B, that is equals to 0. So no work is done in moving the test charge from point A to point B of equipotential surface. We know that a small amount of work done in moving test charge plus Q to a small distance dr over the equipotential surface is given by d of W A to B, work done from A to B, that is F of E, electrical force, into dr vector. So d of W A to B, that electrical force will be Q into E. Q is the charge, test charge, into electric field, it is placed in electric field, into dr vector. So this work done, this small amount of work done from A to B, that will be equals to Q into mod of E dot dr vector, the dot product of electric field and the displacement vector dr. its magnitude. As the surface is having equal potential, or the surface is equipotential, then the work done from A to B will be 0. It means that potential of point B is equals to potential of point A. VB is equals to VA. So dWAB upon Q test charge, that is equals to E dot dr, electric field, dot product of electric field and displacement vector, its mod value, magnitude is there, that is equals to the potential difference of VB minus VA, because these potential are equal, so this will be 0. So this term, work done per unit charge, that is equals to E dot dr, or E into dr into cos theta will be 0. So this term, E electric field into displacement vector into cos of the angle between the electric field and displacement vector, there this will be equals to 0. So this equation will be 0 either when electric field will be 0, or when displacement vector will be 0, or if the cos theta value will be 0. Now here the case is that electric field is non-zero and displacement of the charge is taking place over the equipotential surface. So this dr, displacement vector, is also non-zero. So only one thing is left, that this equation will become 0 until and unless this cos theta will become 0, because these two are non-zero component. Electric field is present and displacement of that test charge is taking place. So this above equation 2 will be 0 when theta is equals to 90 degree. It means cos of 90 will be 0, cos theta will be 0, theta will be 90 degree. It means this electric field vector is perpendicular to the surface vector, or it is perpendicular to the displacement vector along the equipotential surface. Hence there is a note that electric field vector is always perpendicular to the equipotential surface or the displacement along the equipotential surface, dr. So this is one important term we are getting, that electric field is always perpendicular or normal with respect to the displacement vector along the equipotential surface, that is dr. Now for any charge configuration, equipotential surface through a point charge is normal to the electric field at that point. This is important because the equipotential surface through a point charge is normal to the electric field at that point. It means if there is a point charge, then the electric field which is coming out from that charge and equipotential surface, the angle between equipotential surface and electric field will be 90 degree, or they are normal with respect to each other.